Hello students, and welcome to another lesson in algebra. I'm Mr. Graves and want to talk to you today about some more methods in factoring. We have already taught you about how to factor trinomials. Remember, two numbers that would multiply together equal the last, but when added equal the middle. And then we taught another lesson beyond that. We actually had some polynomials that needed to have a greatest common factor pulled out of them. And then once we did that, we had a trinomial that could be factored again. So that was some two-step factoring. Today's lesson, we have a couple of extra different kinds of things that can be done by way of factoring. There is not just one way to do everything in factoring. There's some different methods, and we want to teach you a couple of those again today and try to help you out. But first, let's start with just a review of something we've already learned, and it's the multiplication of two binomials. Now what ends up happening here is we can do FOIL or we can stack them. Well, let's go ahead and do FOIL. So our first is x times x, which is x squared. Our last would be a positive 7 times a negative 7, which would be 49, negative 49. And then what we do is our rainbow for FOIL, our outer and our inner. So we would put this here and then this here, leave a gap. 7 times, or x times a negative 7 is a negative 7x. And a positive 7 times x is a positive 7x. Well, it turns out that there's nothing in the middle because they cancel out, a positive 7 and a negative 7. So our answer here is x squared minus 49. And what happens is we'll go ahead and just erase this and pretend that you did not know how we got to that. Well, it turns out that's a perfect square. So problems like this that are a perfect square have an x squared, or a first term, and a negative 49, a last term, as what we call perfect squares. It has to have a negative in the middle, it can't have a positive. Problems can only work like this with a minus. So what we do is we put our first and second set of parentheses, we put plus and minus, and again we can do that in any order that we want to. And those of you that I've taught before, especially with radicals and square roots, we use the word what. So what times what is x squared? Well, that would be x, and that goes into the first terms of our binomials. All right? And then negative 49. What times what is a negative 49? It looks like it would be a positive 7 and a negative 7. So there's our answer. All right? So x plus 7 times x minus 7 ends up being our answer for that case. I have another one here, x squared minus 16. It's also a perfect square. So we'll go ahead and put our set of parentheses, a minus and a plus. What times what is x squared? X. What times what is a negative 16? That would be 4 minus 4 or plus 4. And again, if you were to multiply those out, you would realize and see that x squared minus 16 would be your answer. And the middle would be deleted because of how it works out. Okay? So those are called perfect squares. They are... We'll study more of those, or go over more of those probably in some homework. Now, we've got another kind of step in our factoring, and we have this binomial here as 5 minus 125x. It doesn't have a perfect square here in it, but there is something that we need to do first. It's a binomial that is set up in such a way where we need to pull out some numbers first. So greatest common factor, we generally break everything down. 5 is just going to be 5, where 125, if we were to break that down, all right, we would have 5, all right, and then 25, and then 5, and 5, all right? And so 5 times 5 times 5 is 125. So min-com means that we're going to pull out the minimum, and we're going to pull out what's common. Well, 5s are all common, but there's only the minimum of 1 5. So 5 becomes our greatest common factor, all right? So now we need to multiply that through. So 5 times what gives me 5? Well, that would be 1. 5 times what gives me 125x? That would be 25x, all right? Now, we notice, or should hopefully notice, that 1 minus 25x is actually a perfect square, all right, in the sense that x squared minus 49 is also a perfect square. Let me take a look here in relationship to our book here. You'll notice that to be the case, all right? Oh, I'm sorry, I did write the problem wrong. That's why I was wondering. This is supposed to be x squared. I was looking at that when I wrote it and realized that can't work out unless that's a square. So, sorry about that. 5 minus 125x squared was the actual problem, all right? So now, 5 times 1 minus 25x squared, this here is a perfect square, except it's kind of flipped around. So here's what we have for an answer. 5 times, and then we write our two binomials, minus and plus, okay? What times what is 1? Well, that would be 1. What times what is 25x squared? 5x and 5x. So our answer actually becomes 5 times 1 minus 5x, 1 plus 5x. This here becomes those two, but we still have to carry down our 5 because it's part of the answer as we pulled it out originally. So don't forget that 5. All right, here's another one, 36x to the 6th z squared minus 64y squared. All right, it turns out that we also have to pull some numbers out to break that down a little bit more and get a greatest common factor. So what we'll do here is we want a greatest common factor to be here, and then we'll have a minus, and we'll see what it comes to. So 36, if we were to break that down, we get 2 times 2 and 3 times 3. 2, 2, 3, 3. If we take 64, and we break that down, we have 32. 2 is 18. 18. Whoop, that's not right. 16. Then 2, 8. Then 2, 4. And then 2 and 2. So 3, 6. 1, 2, 3, 4, 5, 6. We have 6 2s for 64. And we have 2 2s and 3 3s. And so the only thing we can pull out right here is just 2 sets of 2, which become 4. 4 is our greatest common factor. There are no letters because x and y and z are not in each term and they're not common. So that can't be pulled out, okay? So we ask ourselves, 4 times what is equal to 36x to the 6th z squared? 4 times what is 36? That's 8x to the 6th z squared, all right? And then, I'm sorry, let's go 9, not 8, all right? And then 4 times what is 64? All right, 16. All right, and then y squared is what's left over. Okay, now in doing that, we have ourselves a perfect square. It looks a lot more complicated than a simple x squared minus 49, but it's there, and you want to train your mind to look for those. So if we have it, let's bring our 4 down, 2 sets of parentheses, a minus and a plus. All right, let's see what we got. All right, what times what is 9? That would be a 3. What times what is x to the 6th? Well, that would be x to the 3rd. What times what is z squared? Z. All right. What times what is 16? That would be 4. What times what is y squared? Y. So what we have is the exact same thing on both, except the sign is different. And it's the same way here. Remember, you got to look at each term as an actual what times what. Did you know that what times what gives me that? Well, 3x to the 3rd z, which goes in the first term of each binomial. And what times what is 16y squared is going to be 4y. And that goes at the end of each binomial. So if you were to actually multiply these out, you would get no middle section, but you'd only have that. Make sure that you carry your 4 down, okay? This is a perfect square trinomial. And what you want to do is simply look, and of course this is in your book, so you can go over it, but just explaining it by way of the process. Notice what times what is x squared? X. What times what is 25? 5. All right? So we have x times 5, which is 5x. When we double that, or multiply it times 2, what do we get in the middle? A 10x. So because of that, this perfect square trinomial is x plus 5 times x plus 5. Now this is not a minus plus situation, because if it was, we wouldn't have a middle term. But in this particular situation, you look at trinomials, and in your homework on the lesson, you're going to be looking to find the square root of the first and last. Once you put that together multiplied, you're going to double it. And if it equals the middle, then this is what you have, a perfect square trinomial.